Everyone, I guess the mic is on. Yes? Cool, thanks. It's almost 20 past. Let's get started. So welcome to the talk, which is probably the talk that's going to have the longest title of the show. You can read it up there. We're going to talk about microservices, or more specific, we're going to talk about building serverless applications and how that intersects with microservices. And very specifically, we're going to talk about WebAssembly and a framework called Spin. So my name is Mikkel. I work at a company called Fermion. Fermion is a year and a half old. And Fermion is a company who set out to pioneer the next wave of cloud computing. That's sort of the tagline that got us a bunch of money to start building on some awesome technology based on WebAssembly. As you can see from up here, I have a past in building products for cloud computing in Microsoft. And that's sort of the trend throughout the team at Fermion. Basically, it's a couple of Microsoft, previous former Microsoft employees who got together and started this whole new thing to revolutionize cloud. So in the next hour, we'll walk through these 3 questions. What is this whole WebAssembly thing, and what is the Spin framework? How should you use it? When should you use it? And like the bold statement is then like how this will change everything. I think I have at least 2 things that will change, but that's close enough. Okay, so let's start it with a few things that is good to know about WebAssembly. WebAssembly is a specification of a binary instruction format, which is designed as a compatible compilation target. Okay. That could be a Java virtual machine. that could be a lot of different things. But the main thing to think about here is that there are some design criteria around WebAssembly, the specification, to have a common compilation target that can be ported across operating systems and processing architectures. It originates from the browser, so WebAssembly was built as a specification to enable you to use other programming languages than JavaScript to interact with the browser APIs. And what's interesting about WebAssembly is that you can also use it outside of the browser now. And we'll get more into that, and I'll show you that with Spin. A thing to be aware of around WebAssembly is support across various programming languages is emerging and is stabilizing. I mean, we could have inverted that sentencing and see this is still early days, right? That's really what I want to convey with that. And if at any time I talk about WASM, it's the same thing. WASM, WebAssembly, WASM, whatever. So just be aware of that. So when I talk about this common compilation target of WebAssembly and the binary format, what does that mean? Well, basically, if you go from having written some code over here and to get that running, what we do is we use various tool chains across various programming, which differ a little bit across the programming language how this is actually done. But you come from your source code down to this binary WebAssembly format. And I think there are around 3 different ways that programming languages deal with this today. And on top of I can remember 2 of them. I can actually remember the 3rd one. But you would have like low-level systems like Rust and C who will just directly compile into the binaries. Then there are things like JavaScript, sort of the interpreted languages, where today a lot of the solutions are really to compile the interpreter and not the actual script you have. So there's a little bit of overhead in some of those languages. But I guess this is just touching on this point that, depending on what programming language you choose to use to build WebAssembly, there is a various degree of support and efficiency at this point in time. But once you have that compiled WASM file, the binary file, this is now the same specification irrespective of what programming language you came from, which means that when you need to run these things, all you need is a virtual machine. And this is not virtual machine in the sense of a thing that has an operating system. It's a virtual machine in the sense of like a Java VM or something like that, right? That will enable you to run that WebAssembly module. So to touch a little bit upon this whole runtimes thing and browser versus outside of the browser and these runtimes and what's available there. On the left-hand side, we have what I call the JavaScript runtimes, which is sort of the stuff that works or were built with to work within the browser. So you have obviously V8, which is used across Chromium browsers. You have SpiderMonkey, which is a Firefox thing, and obviously then you have Node and Dino, which are outside of the browser, but they're all JavaScript runtimes. And really what that means is that any WebAssembly program you want to run inside of these runtimes, you need to have a certain layer of JavaScript glue code to help interpret whatever WebAssembly APIs you call down to the actual APIs that are available in that runtime. So that's sort of the old world WebAssembly, or that's where WebAssembly came from, where it originated. On the right-hand side, you have this thing that I call the WASI runtimes. So WASI is another standard within WebAssembly, which is an acronym for WebAssembly System Interface. And what it really means is that in the world of the WASI runtimes, you now get a different set of APIs. And that APIs is APIs that would resemble an operating system. It's not POSIX compliant, it's not necessarily meant to be POSIX compliant, but you get access to things like files, network, eventually. We don't have socket support yet, but files, networks, constructs like environment variables, clocks, and other things. So stuff that you would normally write to run as a service on a server, you could start writing against the WebAssembly system interface. And there's a bunch of runtimes over here. Wasn't Time by Bytecode Alliance is the one that we use. We also heavily participate in Bytecode Alliance. Then you have WASMED, which is a CNCF project. So it's a project under the Cloud Native Computing Foundation. And Node.js actually has some experimental support for WASI as well. And to just walk you through what this whole WebAssembly in the browser means and how what the story is for the browser and how you can mix and match programming languages. I think one thing to mention there is that if you've heard about WebAssembly and browser and some of its, some of the good stories there, you probably heard about how companies like Figma and Adobe are using WebAssembly to create these very emerging experiences, actually build real applications inside of a web browser that perform very, very well and are very small in terms of how much you need to download and run them. So what I have is just a code example here where I'm showing you some Rust code. And whether you know Rust or not, the thing that I'd like to point your attention to is around line 5 to 7. You can see how we actually have APIs here that resemble HTML, or how you interact with the browser, right? So we're able to get a document from an inner window, we're able to get a body, and then we can go into that body in line 9 and we can start creating HTML elements, right? We can do that from our Rust code. And the way that works is, once these things compile down to WebAssembly, and there's a whole tool chain enabling you to create what I mentioned, this thing, the glue code, which basically means there's some JavaScript that intercepts those APIs. So you would have some JavaScript here where in line 11, I'm actually calling a calculate function that you can see I have in the bottom of my Rust code, right? So I'm able to call Rust functions from my JavaScript code, and I'm able to, from my Rust code, via some of the glue code, go in and manipulate my web app. So this is a browser window, but what you can see is what's actually in the window being rendered are just coming from these random pieces of, not random, but these different programming languages and different source codes, right? So I hope that sort of gives you an idea of, at least in the browser world on WebAssembly, how it opens the opportunity for you to provide, provide applications where you can leverage other programming languages than necessarily JavaScript. We have actually assembled on our website, there's a link at the bottom, there's a QR code over here, a good guide to sort of give you an overview of the language support around WebAssembly. So when we talk about browser and WASI, those are the difference between the runtimes, and then we have SDKs for our framework, but we'll get back to that a little bit later. But if you're interested in learning more about the language support, this is a good resource. Okay, so that was an introduction about what WebAssemblies are. Any questions about WebAssemblies? We can take those afterwards, if not now. I do want to say Sohan, my colleague who's in the room somewhere, I can't see where, oh, he's right in the back. Anyways, we have a workshop later today. So from 3 until 5 in room 4, we're running a workshop where we'll guide you through a lot of the WebAssembly stuff and working with Spin. So if any of this catches any of your interest, please show up there. Okay, let's talk about how and when this thing makes sense. And this is not WebAssembly in the browser, right? Now we're going WebAssembly outside of the browser because that's what I'm interested in, and that's what we do. But having that, not legacy, but let's say, having the well, yeah, having the legacy of being designed for the browser. There are 4 very principled sort of design criteria for WebAssembly, right? Anything that needs to run in this browser has to be small in its binary size, because you rarely execute things from disk unless you have them cached. You actually need to go and fetch the program over the internet, which means the smaller the size, the quicker you can actually get to execute. It has to start off really, really quick, because it's probably part of a, there are these, I think there's a Google app or thing called Lighthouse that helps you measure, like, the time it takes for your website to start rendering. And it's a thing in the front end and, experience world of web pages to get as quickly as possible to start rendering the website, so that, the small attention span we have, people don't start, going to other tabs of whatever they do, right? So startup time is really, really important for WebAssembly as well. Portability, obviously, we work on the internet. We have no idea what browser a user is using. We have no idea what processor sits underneath the operating system where the browser runs. We have no idea what the operating system is. So the same WebAssembly needs to be able to run across all of these things. And finally, everything that runs in the browser is non-trusted from the local machine point of view. So we need to make sure that we execute these things in secure sandboxes. So anyone in here who writes stuff that doesn't run in the browser would like all these things for their services as well, right? That's what we can get. That's what we can get with WebAssembly system interface for running services outside of the browser. So to give you some examples of these things, if I have a hello world written in Rust, that's a 2 megabyte binary size, and that's a non-optimized. That's a binary that's actually portable. If I do an ahead of time compilation version of that, which means I can take the binary format and I can compile it to a specific processing architecture and operating system, it's a 300 kilobyte file. If you write an application in Spin, that's an HTTP API, the just-in-time compilation version of that is a 2.3 megabyte file. Ahead of time is 1.1 megabyte. These are things you would normally do in containers, right? If you do stuff as services. So there's some size comparison here. I'll get into that later. Startup times, compatible with natively compiled code. It's only 2.3 times slower than native, but the trade-off there is obviously what you have on the left-hand side, the binary size is right. You can get the speed down if you do the ahead of time compilation stuff, but if you keep in the portable format, there is some performance penalty, but it's really, really close to being same performance as native compiled code. Build 1 runs anywhere. Same JIT build works across operating system and platform architecture. So the 2 megabyte binary that I have in the top, if I build that on my Mac, I could go running on a Linux. That's an x64 architecture. This is an ARM thing, sorry, what I have here. So all of these things, like, you can move them around. And finally, security, we have these sandboxed execution environments where memory doesn't leak between, or memory isn't accessible between the individual WebAssemblies we run. And on top of that, there's a system around WebAssemblies called a capability, or it is a capability-based security model, which means that whenever you run a WebAssembly, if the WebAssembly needs access to resources outside of its sandbox, you need to explicitly state that at runtime. So I have a WebAssembly that needs to write a file. If I just run the WebAssembly, it doesn't get access to the file. Even though that I run it in a user context that might have permissions to read that file on the machine I'm running it on. But I have to, as I run the WebAssembly, specifically specify which part of the file systems do I want to open up for the WebAssembly as it runs. And that's a really, really powerful feature in this scenario. So I hope, again, these are some of those things that sort of, we can get from WebAssembly and that we can build up on. And then if we take that and look at, put a little bit of perspective in terms of the type of use cases where WebAssembly system interface, which means the WebAssembly running outside of the browser are really good for, then we have these 4 things that I just mentioned sort of as a foundation for all of this. And truly, I believe anything, around developer experience, having to work with stuff, or an operational experience, that's just, things are portable, things are small, and all these things. There's a huge opportunity of benefits. How many in here are on a daily basis doing development and using containers on the local machine? Okay, fair amount of people, right? There's a certain amount of overhead in having to do that, right? The container layers and the size of those things, the startup times and dealing with all of that. you can actually get to the same place with WebAssembly, but just scrap all the container stuff. I'll show you that in a minute. So yeah, 3 use cases that we believe sits on top of this, where this fits really, really well. So cloud, because that's where we are at, the space we're in, and particularly these things like functions as a service frameworks or serverless frameworks, which is what Spin is. Then there's something called the component model in the WebAssembly world. I'm not going to touch upon that today because we simply don't have time to do that. But I'm going to talk about it anyways. So the component model really is a way for you to be able to what do you call it? I've lost the word in English right now. You can compose applications, that was the word. You can basically compose applications from multiple WebAssembly modules. So consider a WebAssembly module could have the equivalent of a main function, which means I can run it, and it just runs its main function, and it may or may exit, or it may stay up, whatever. It has some notion. You could also build a WebAssembly that doesn't have a main function, but just have a bunch of functions that it exports through a set of, with a function signature that's defined through a set of primitive types that is at the WebAssembly layer of the specification, which means I could build a module in Rust, export some functions, build a set of function signatures that my TypeScript WebAssembly would understand, right? So I can have these WebAssemblies written in various programming languages that actually start, imports and export functionality between each other, which means that, I can start compose these applications by having all these WebAssemblies sort of chained together and figure out who's going to resolve what dependencies that I have and stuff like that. Very fancy stuff. Go and check it out if you want to. I'm not going to dive deeper into that because it's going to take the rest of the time if we would do that. But there's a lot of great stuff in cloud happening and great opportunities there. The plugin, a lot of scenarios people have for creating these user-defined functions for databases. So you can see people creating WebAssemblies that they actually go and extend their databases with, so you can build a particular function that you can run when inside a database query. So there are some companies working in that space, but also if you have a SaaS platform, like think anything, I don't know, HubSpot, CRM type of systems, whatever it is that you provide as a platform provider, you can have your customers bring custom code through WebAssemblies because you have the secure sandbox, because you can define those interfaces like things in a component model and all of that. You can actually in a secure way host untrusted code within your platform. Is that what you want to do? So that's sort of the plugin space. And finally, IoT, there's stuff around system resource uses, no dependencies you have to carry along, because all you need is the WebAssembly runtime. So those are sort of the 3 highlight use cases that I believe WASI has a bright future. Okay, so moving on to what it is that we do at Fermyon. First of all, we work a lot upstream in the WebAssembly space. So a lot of the programming language support, building component model. The lead developer was in time the WebAssembly runtime that we use, and that is owned by the Bytecode Alliance, is also a Fermyon employee. So we have a lot of stake in what's going on in sort of the fundamentals of enabling all of this. But the projects and the product that we build, because we're a company and eventually we're meant to make money, I guess that's how things work, we also have to have something that we can sell. We created an open source project called Spin, which is basically the foundation for the serverless experience that we have. I'm going to spend the next at least half an hour demoing that for you now, so you can sort of get an idea of what that is and how that works. And then we build sort of a commercial offering, which is just a cloud, which means that if you build a Spin app, just give it to us and we'll run it. I'll show you in a second how that works and how some of all of these benefits that I laid out now sort of come together in this experience, from local development to how we do things in our cloud. Cool. Yeah, let's not dive into the marketing stuff underneath. Okay. Is the fun big enough for everyone? Okay, cool. So if I want to get going with Spin, all I need to do is I need to install Spin. And I can do that through Homebrew because that's nice. If you're on a Mac, if you're on other platforms, we have install scripts and stuff. Basically, you go to GitHub Fermyon/Spin, and there you'll find the repo, and you can download our releases there. I have already downloaded Spin to my machine. I have the latest version, 1.4.1, which was built mid-July. And the first thing you can do with Spin is you write a command called spin new. So Spin is a lot of things, right? There's a CLI experience, there's some hosting components, there's templating system, there's a lot of stuff. We'll get into that as we go along. But as I write a spin new command, I am presented with a list of templates that I have on my machine that I can use to start building out my application. And the thing that I want to do in this demo is I actually want to build an application that has a little bit of a front end and two backend services. The front end can talk to the backend services. The backend services has some system state. And I guess that's a pattern that covers a lot of scenarios, right? Just in its raw form. So the first thing I'm going to do is I'm going to do a spin component using a template called HTTP Rust, which basically means I'm going to implement an HTTP request handler using Rust. So let's call this application, let's actually call this Copenhagen, whatever. We're going to set a base for where we're going to listen to stuff. And because we're going to build this out having multiple components, I'm going to say this first request handler is going to handle all the requests that's going to end up on a path called whatever hostname / Rust. It's going to be forwarded to my component here. Okay, so let's see what we have. So in this folder called CHP, we now created some Rust source code. We have a cargo toml file that will, the Rust package management thing. We have a spin.toml file that is describing our application. We'll look at the spin toml file a little bit later. But this is really the boilerplate of an HTTP handler for Spin written in Rust. How many in here know Rust, like would understand this code? Few. Okay, I'll try to walk you through this. It's fairly straightforward. The code is not that complicated. I have a bunch of use statements in top, so things that I import. You can see we have an SDK and various functionality in there. Then in line 8, there's a macro, and in Rust, what this means really for your function is that this tells Spin, the host runtime that we'll use when we run this thing, that this is the function you need to call when a request comes in. That's basically all it does. And you can see that the function signature that I have down here takes a request, which is an HTTP request, and returns a response. In Rust, those things are wrapped in results, so we can check whether things went well or not. And basically what we're doing is going to print a line with the request headers, and then we're going to send an OK, HTTP OK response with the status, some headers, some body back. Okay, let's go and try this. I need to figure out where I ended up here. I think this is it. Oops, sorry. That's not the one. I have too many of these right now. I had another one on top of that, the dev fest. There you go. Okay, that should be it. Okay, what I'm going to do then is I'm going to run a command spin build, and what spin build is it's going to start compiling my Rust code to WebAssembly. The spin build command is just a tool chain in the CLI, where, as you will see later, as I start building out my application with some TypeScript and other stuff, there's just a way in our manifest file where we sort of tell what the build tool chain to use, but I can show you that in a second. But now we build the application, and obviously the next thing you do is you spin up your application, which means that now we start this application. We have it running, and we can go and call this on port 3000, and there you have the response. Okay, that's it. We have an HTTP thingy going, and we can start building on that. So that was quite easy, right? All I needed on my machine, I needed obviously the Rust toolchain to be able to compile Rust, and then I needed Spin. We're taking care of the rest. Let's try and build something a little bit more meaningful, because as I said, normally in these applications you want to store some state and things like that. If this could have been a webhook or something like that, right? You could have just mingled with the data coming in. So let me go over here, and I'm just going to start and copy pasting some code in, so you're not going to have to deal with me trying to write stuff live. I'm going to start adding a new dependency on an HTTP router, because that just makes it more easy for me to sort of to handle the different requests that will come into my application. So what I will do now is I'll just go ahead and delete a bunch of stuff. I'll go ahead and paste a bunch of stuff in. Let's see how that works. Okay, that worked well. So the code that I've pasted in now, again, we have another macro here. Again, this comes from our SDK to create this router that just makes it very easy for me to sort of branch out depending on the request coming in. If it's a GET request, what do I want to do? If it's a POST request, what do I want to do? So in this case, if it's a GET request, I'm going to forward everything to a getStuff function. If it's a POST request, I'm going to forward things to a setStuff function. So let's go and implement those down here. Now what we're going to do in these two functions is we're going to persist some data. And the reason why we want to persist data, let me just get this in. I'm going to put in a few more using statements here. So we have this thing called a key value store, which it's a simple store technology where basically you put in a key and you add some arbitrary value to that, right? So you kind of know these type of patterns like you would do with a Redis key value store database or something like that. And the reason why you want to use these key value stores in Spin is that the HTTP handler, the WebAssembly component that we built here, that thing doesn't persist any state between requests. So whenever a request comes in, the host that runs the Spin application finds the WebAssembly module, loads the WebAssembly module, hands over the request being handled. As soon as the request is being handled, the module is going to be unloaded again. So you don't have any memory between those requests where you can store session or other types of things in. So typically if you want to persist things, you need a key value store. Now let's get back, we'll get back to that whole loading thing because well, no, let's do that now. I talked about the startup time, right? Like these things start in less than a millisecond. So there's no need for us to keep things around because the usual pattern for most of these types of applications is that you either have some very high throughput applications and you design and you build for that, but there's a lot of apps that doesn't necessarily need to, handle that many requests per second. So if we can serve a request in 10 milliseconds and we have to serve, let's say, 20 requests per second, like 80% of the time we don't have to be loaded. I think I got the math right. Something around that, like that, right? And we can do that with this model. And because we have these quick startup time, and you think, well, typically when you think about serverless models, things like Lambda or Azure Functions, you have to deal with cold starts. We've eliminated that with this technology, right? It's not a thing. So we'll just load and unload whenever it's needed. Things don't run unless you actually need them. So that's why we want a key value store. That's one reason why we want it. We probably want to use it to store some, application data as well. So let's go ahead and implement those two functions, the set and the getStuff functions. I think I got most of that. Too much. Okay. That's what I need. And we'll just go to the end of this one, paste that in, and hopefully things work as they should. Okay. So a few things I want to point out here. Let me just go at the top. I need a params. That's the one I need. So I just need one more thing and we should be good. And we can go back to the function down here. Okay, let's look at this function where we set stuff. So the API that we built in is fairly simple. You instantiate a store, you open something called the default store. I'll show in a second what that is. We'll unwrap an ID that we require from the URI in there, and then we'll check if something exists in the store, if that ID exists on line 30. And basically, we don't care whether it exists enough, we're just gonna set it anyways, and that's what we do in line 36. So store.set, put in an ID, and then I'll just take whatever is in the body, and I'll throw it in there as a string, and that's it. So now I persist the data in a key value store, right? And the equivalent, when I go and read things, I open them, I use another store function called get. I get that ID. If it is what it is, if I get an OK back in line 49, I'm returning the value. Otherwise, there's some error handling down here. And there's like the worst ever error code, like 500, which means you can do nothing about it, at least if you're on the client side. But we can return that as well. Okay, so let's try and do this. I'm going to use another spin command down here. I'm going to use a spin command called spin watch. And what watch does is it watches for any file changes as I'm coding along, right? So if I went up here and let's say we're going to change some error message here. I'm going to write my file. You can see in the left-hand corner that everything just rebuilt, right? So from a developer experience point of view, just have that running in the background, and you can mess around with your code, go and change, and everything will be updated. Okay, let's try and post something into this. So we're going to do a curl post. I think I have something. Yeah, there you go. Hello, Copenhagen. Let's say this is going to be ID1. Oops, access denied. Okay. Remember I talked about how WebAssembly has this concept of a capability-based security model? No one told the framework that this application would have access to a key value store. So there is just access denied. Okay, it's an easy fix though. We can go into the spin toml file, and we can start diving a little bit into this one. So this spin toml file is just, call it a manifest file for application. There's a bunch of metadata in the top, line 1 to 6. One thing to note is that line 5, we have this concept of triggers. That's the type of trigger that will trigger the components we have down here. In this case, it's HTTP. And then from line 8 and on, I'll start listing out all the components that I have. So the component we created, we called it, it has an ID, it has a source, and this is the first time you're going to meet a WebAssembly here, right? So you can see there's a WASM file. What that means is that my framework, my spin framework, knows that from line 13, that any HTTP request coming into the Rust/Rust route will be handed over to that WebAssembly. And then from line 14, I have some of that build stuff. So when I run a build command, you can see those Rust builds going on. But actually, between line 10 and 13, it could have came from anywhere. Like the WebAssembly could have been Python, could have been TypeScript, could have been JavaScript. We don't care at this point in time because things have been compiled down to that binary format that is portable across operating systems and so on and so on and so forth. And it's the same irrespective of where it came from, which means that at this point, we don't know, we don't care whether that is Rust. Okay, we'll go a little bit into that later, but what I'm going to do here is I'm going to give this application access to a key value store, and I'm going to use we have this convenient feature, we call it, where you can just define a default key value store. That's it. So let's go back and see. Hey, works. We are now data stored. Okay, we can go and try and get that. Let's go back and do this and say, hey, hello, CPH. Isn't that a nice developer experience? Like I didn't have to start a Redis container or anything, right? It's just there. It's so nice. I like it. Okay, cool. What's actually happening under the hood here, we can go a little bit under the hood, so I said that default is sort of a convenience and a magic thing that we have. We definitely have engineers that doesn't like it, but that's okay. But what we have is in, sorry, to go back one. What don't I have here? Let me just make sure. Oh, there you go. Okay. So I have this .spin directory in here. And if we peek a little bit into this directory, you see a few things. First of all, we're actually storing every log. So everything's being output to standard out on arrow in a log directory. So you can find that. And then you can see we have a few SQLite databases. So what we've done is, for the local developer experience, we basically implemented a SQLite database with a table schema to handle key values. So you don't have to deal with it. It's just there. You just write that file. It is very convenient. It's very easy. Now, you obviously don't want to use that for anything beyond your developer experience, right? So two options. You either hand it over to our cloud and we'll take care of the rest. It will be even more magical than this. We can actually do it right now. That's it. No, wrong directory. Damn it, moment totally destroyed. There you go, okay. So you have the option, just give it to our cloud and we'll take care of the rest. And if you don't want to do that, or you want to run it somewhere else, there's a concept of a runtime configuration. So when I start my spin application, spin up, I can provide a configuration that tells me whatever key value store I named in my spin toml file actually maps to a Redis endpoint or something else, right? So if you really want to run Redis in a container, you can do that, and you can have your spin app talk to your Redis. We do have a Redis provider implementation for this. And while I was talking, our application is now running in the cloud. And if we try to get an ID, we didn't get an ID, but we should actually be able to post to this. So let's go and find our post. And let's go ahead and post to cloud. There you go. So if we go back, there you go. That was nice. That was an even nicer developer experience, right? We actually built an application that runs in the cloud that has persistent store and a key value store. Try do that with Azure. Sorry, I used to work in Azure, so it's fine. Okay, cool. But it gets even better than this, because there's actually a new dev who just entered my team. That developer does not know Rust, but the developer loves TypeScript. And this developer has to implement some service that needs a relational database. Da-da-da. Let's see what happens. So we can go back into this application, and I need to figure out if I'm in the right place. Yes. Okay. What do we do? Oh no, there's actually another thing I want to do, because I have an operator on my team. This became a cosplay thing, I think. No. Anyways, so we have this operator on our team, and actually want some access to that key value store, because like what's actually in that key value store? It feels a little bit hidden-ish. Well, as you can see, these components that we defined in the spin.toml file are just references to WebAssemblies, right? That's all they are. So why wouldn't there be an experience where I could just pull down a random WebAssembly from the internet and make it part of my application? Well, guess what? You can do that. So we have this thing we call the key value explorer, which one of my colleagues wrote, and now I just added that to my application. So we can go back, do a spin up, and you can see we now have another component. I can go to that component, and this is secured by random username and passwords in basic auth. That's fine. We can improve this once. But this component just implements a web UI where I can see the data I put into my key value store. And I can actually go and add in some new stuff. Hello from KV. Let's put that on the 3, 4, and then we go over here and we try and get that. There you go, right? So it's the same key value store we implemented. So what happened there? Well, let's go up, and we probably need to, whoops. Let's just get out of this guy. Let's go back and open the, I don't know what the spin tom is. I got confused with all the directories I have. But what you can see what happened when we ran the spin add command is that we added another component in this toml file. And this component now pulls in a WebAssembly from GitHub. It has a digest, right? So I can go and make sure that it's the right WebAssembly that I'm running, not some random stuff. So you get a little bit of this idea when I talk about composing applications, right? You can pull in these different, this is not the real component model, but it's sort of the same idea. And this has access to the same key value store as my application. So they actually share access to that key value store right now, right? Okay, that was an easy scenario. Now our application has an operator interface, or whatever you want to call it. Okay, back to that new person on our team who wants to build a TypeScript application. So let's go in and do spin new, and let's look at the list. And wait, there's the TypeScript HTTP handler. You can call that TSS. That's okay. Base is the same, and we're just going to serve things off of TS. So if we go back, and I need to do one small thing, because this is TypeScript. JavaScript, NPM stuff. Okay, there you go. And we can go back and do spin watch. Part of what we're doing here is, hey, what happened? That did not go well. Let me just check one thing. Did I spin new and not spin add? I probably did. Let me get rid of that thing. And let's try again. So yeah, I did a spin new. It's funny, someone actually gave me the feedback yesterday. We need to warn about that. Okay. Let's try again. I can get to rename it correctly this time around then. So now it's a TS component. There you go. So if we then go into that and we do our npm install again, then if we do a spin watch, you can see we're now starting to do some JavaScript compilation. At least there was some .js thing going on up there, and part of what we've done is we built a plugin for Spin that just helps you do the compilation. I quickly mentioned at one point that JavaScript, the way that JavaScript works with WebAssembly is that we have the interpreter compiled down to WebAssembly, and we then can put the script in there. It's not as efficient as in other languages, but it works. And if we go back and look at the TOML file now, we should have a third component down here, which is a TypeScript. And you can see from 29 to 31, it's the same pattern with the Rust, right? It ends up being a WebAssembly. It's served on a specific URL path, and there's a command to build them down here. And if we go and open the file, our source file, there's an index.ts, you sort of get the same pattern of how that HTTP handler is implemented. There's some SDK stuff we import, we hand over the request, we return hello from the TypeScript SDK. So we should be able to, in the curl window, to do this, and there you go. Now we have an application serving HTTP requests in a combination of Rust and TypeScript. Okay, I promised I wanted to get some SQL data in here because that's also what we want. And guess what? We actually have, I'm just going to take the whole piece and paste in here. So let me do this, and delete, and we can paste stuff in. I'm importing a SQLite interface from our SDK. And you can see in my handler, I'm opening a connection, again, to a default database in line 6. It's the same pattern as with the KV store, right? There's a convenience of a default SQL store and runtime config. You can point it somewhere else. I actually think the runtime config for SQLite is not quite there yet. And then I just start executing SQL commands. I get a result back, get it into a JSON thingy, and then return that to my client. But if you have listened very, very carefully, you know there's another thing I need to do right now, which is I need to give that component access to a SQL database. So let's go over here. Whoops, that's not what I wanted. Let me just get out of this guy again. Let me try again. So let's go to our component. And I want to go up here, and I just have like, hey, there you go, SQL databases, default. Okay. And there's one last thing we need because we don't have a database schema, obviously, right, in our database at this point. But what I can do is I can create a file. Let's call that db.sql. And I can paste in, I can have some SQL sitting in here in this case, just create this table if it doesn't exist. It's a to-do thing, it has an ID, it has a description, it has a due date. And then when I'm gonna run my spin up command, well, I can actually do spin watch. I can point to this file. Let me check where it went. It went over here. I can point to this file so that once my application starts, it actually executes that SQL statement against my default SQL database. So now I should be able to I'm just going to insert some data as well, just to get everything up and running. I need to be in the right directory. That was the devfest thingy, and then in CPH, and this is where I have my spin. Okay, so we should be good. So we could do a SQLite command, and then within that database that I have, we should be able to insert some data. There you go. Okay, so I just inserted some data into the database, writing a query directly against the database, which means that if I go and hit that endpoint, you can see whatever data is in the SQL database now comes back. So same story as key value, right? There's some convenience feature around the default and everything, and it all just runs there. TypeScript, Rust, relational databases, key value stores. Like, I mean, I didn't write the code right now, but from a dependency thing, from the developer experience, everything is just there locally. And I hope you sort of get an idea of how fast things actually work, like the startup, like how fast these things respond when I do a request against them and all of that. So the last thing I want to do with this application before we get everything into the cloud is, I do want to add a front end because that makes my application a little bit more fun. So we can go back, and now I need to be in the right place and do a spin out again. And we actually have another component that we built, which is basically just a file server. So what the files, I think the file server is written in, I don't remember if it's written in Rust or Go, but any of those languages. But what that enables me to do is just serve some static content over HTTP. So we can have, let's actually have that listen on the root, and then we'll just create a directory called assets. So I can create a directory now called assets. And if I go into assets, I should be able to create an index.html file, and then I can paste some data in there. Just hang on a second. We should be able to do that. So how do you know how you create a front end when you want to do a demo? What would you do? You know what I did? I asked ChatGPT. It was quite fun. We had a fun conversation. It became a little bit snarky, by the way, because you know what the title of the HTML document is? It's a backend service demo. I did not tell it anything about that I had to use this for a demo, but it kind of, felt like you're probably going to do a demo. I'll give you some demo stuff. So anyways, so I got this front end from ChatGPT. Works pretty well. I should be able to now, if I got everything set up correctly, let's go and do a spin watch. I didn't run the SQL command this time because it's already there. And there you go. Let's try and call the backend service, and we get stuff from the key value store, we get stuff from a SQL store as well. Okay? So I think 25 minutes ago, I told you that I would build an application with 2 backend APIs and a front end working together, have some persistent storage, both relational database, key value store, mixing different programming languages, get all of that running in a serverless fashion. This is serverless. And I think the other thing that we don't have, let's deploy this whole thing to the cloud, by the way. Now I'm just going to upload this whole application, and I want to move from that local developer experience, and I want to have it running somewhere when people can get to this. And hopefully, very, very soon, we have this whole conundrum of an application with all the databases and dependencies and everything up and running. Besides from me not writing the code, actually, as we did this was a half an hour exercise. And hopefully, in a little bit, that application should be ready. There you go. All of our endpoints. Let's see. Did we add anything up here? Yeah, we added one. I don't think we added anything to the other one. No, we didn't create the, I didn't migrate, I didn't do the table definition in the SQL database and cloud and all of that. So I have to do that now, but there are simple commands to just, I think it's spin cloud deploy, SQLite points to my SQL statement, that would be run against the database. I can create my table and all of that. Cool, you like it? Yeah? Awesome. Okay, that was this slide. So I showed you this spin framework. Again, Spin's fully open source. It's a conundrum of things. There's a CLI, there's the host component, there's the application model, there are the SDKs and all of that. But think about Spin as a good place to go if you want to build web applications and you want to have these, small functions or microservices handling various pieces of your code. You can, you have that single binary tool, you support the many languages, it's very easy to get started, no boilerplate required, you can work with data very seamlessly, and you can get all of this up and running in our cloud. There's one thing I want to show you, there's actually one thing I want to show about cloud, because I talked about cold start, right? And I know we just deployed this application and it's sort of rendered instantly, and that's fine because we just deployed it and we sort of hit it, right? I have another application running in the cloud somewhere. This is an application that was created a while back. Let me just go and refresh this. What I'm showing you here This is just a UI we have for our cloud. So you can see I have a bunch of applications running up here. This is one of my applications. And if I look in the past 7 days, you can see I have a single request. That was actually yesterday because I was doing this demo somewhere else. But yesterday, I hit this application. Now, in a case of Lambda and functions, for instance, when you host these type of functions, serverless functions in the cloud, you can either pay to keep them hot, or you can be lucky that they stay hot for a while, right? Because there's a bunch of stuff with the dependencies and how these clouds work that they need to take care of. You remember how I told you we don't run things, right? We just respond to requests. Like we go and pick the WebAssembly that needs to handle the request, and in our cloud it's just a big pool of WebAssemblies that were deployed. We have the mappings between the URIs and whatever comes in, but all we have to go is fetch that WebAssembly, which is a small binary that starts up really, really fast, and we just serve the request. So this application that I used the last time yesterday evening is a webhook that's hooked up with our Slack. So if I type this in my demo Slack thing here, what actually happens is Slack is going to send requests into my application in the cloud. In the inner workings of our cloud, we need to go and fetch the WebAssembly, load it, handle the request, send a return back to Slack. And this is the moment where I always have to say, don't blink. Because, there you go. That was cold start. Okay? So, you know, when we talk about pioneering this next wave of cloud computing, and we talk about how, you know, having these small functions, these small pieces of code, microservices things that you want to juggle around with. I think what we're at with Spin is, you know, just write the code, have fun on your local machine, don't think about all those dependencies, throw them into the cloud, and you don't have to care about anything but that. You don't have to care about, I'm going to pick a little bit on Kubernetes now, is that okay? Yeah? There's no YAML involved, right? There's no auto-scaling involved. There's no, I need another operator thingy to have containers not run when I don't need them, because I don't need them to run 24/7. Don't think about it. Just do WebAssembly. Okay. What's elsewhere? Talking about peeking in Kubernetes, you can also run WebAssembly in Kubernetes. Because why not? There is a project in CNCF called Run WASI. And basically what Run WASI does, it enables this new type of workloads. Like, I know it's easy for me standing here and say, just, you know, write WebAssembly, use our cloud, and don't think about Kubernetes, but I bet that at least half of you have to deal with Kubernetes on a daily basis. Is that sort of true? Yeah, probably. But it also means that you have a lot of code that is already written and already runs really, really well in that infrastructure. And, you know, we can't ignore those landscapes, obviously not. So together with Microsoft, a company called Liquid Reply, and other companies, this project has been bootstrapped that actually enables you to have these WebAssembly runtimes run inside your Kubernetes clusters. You can take the WebAssembly workloads you have and deploy there, and basically have containers and WebAssembly modules living side by side in harmony. It's implemented through Containerd. If you're deep into Kubernetes, you can dive into this. But basically, Containerd had this concept of the using runc to run container as the container runtime. This is where Run WASI sits in that sort of architecture. So it's a shim. And basically, Run WASI supports a variety of runtimes for WebAssembly, among those Spin, meaning you can actually take your Spin application, create an OCI, create a Docker file. It's the same, whatever. You create a Docker file, you put your spin.toml in there, you put your WebAssembly in there, and I'm just going to forward to this one. We'll go back. You can see on the left-hand side, that's the Docker file with the Spin application. You start from scratch. From scratch means there's nothing. Right? The container is just a bunch of layers of additions to the file system, right? Which means the first layer you have is nothing. Then you add that spin.toml file, can't be that big. And then you add your WebAssemblies, which were small, right? Because web and all of that. Now, if you compare that, which is that hello world is an implementation of an API in Python. On the left-hand side, right-hand side, I have a Docker file that is from, I think it's from Docker's repo that shows you what sort of the foundational Python Flask Docker file looks like. That starts building on a file system that has a framework, where Python 3.10 is installed, right? Then it copies in a requirement stuff. It installs a bunch of requirements, right? So you can see all these file systems, and that container starts building up before you actually get to your Python application in the end. And if you do a file comparison, and I've been measuring this in my PowerPoint slide, this is the size of that container. This is the size of that container. And in numbers, we're talking 23 megabytes versus 550 kilobytes. So even in that world, WebAssembly has something to offer in terms of how these things work. Okay, so I promised to talk about how this will change everything. If you're not convinced yet, I have a few slides to convince you more. I have at least two things. Fixing serverless. So yeah, we are fixing serverless. We're getting rid of cold start. We have an awesome developer experience compared to what you do with those other languages today, which are, or frameworks, which are typically proprietary frameworks, which was my last bullet. You can mix and match languages in your application. You don't have a dependency on a platform because whatever you build runs anywhere, right? And what that leads to is the use cases for which you can use a serverless framework just expands beyond imagination, let's say that, whatever. There are probably limits. We haven't found them yet, but just don't think about using Spin in comparison to using Lambda. Think about using Spin to write your applications, right? And to go back to the whole title of this talk, yeah, there is less complexity in doing these type of microservices applications now, because any request that your function needs to handle, and I showed a lot of HTTP requests here, it's like, you know, it's a fresh start every time you code. You don't have to deal with like state between things and whatnot. So just a whole bunch of complexity that is taken away from you there. I do want to mention that even though I showed HTTP requests as being sort of the input, the triggering for these components, we've also provided triggers for Redis. So you can have components that are basically watching. The component is not watching. The host component is watching a Redis queue. So when things entering the Redis queue, that will be the trigger for the component. We have, in our community, we have people who contributed components for other type of messaging service like SQS, and MQTT is also a trigger that is coming in now. And then a second point with the clunky containers, I think I made that point already. And if you want to get some inspiration on this, we have this thing called a spin-up hub, where basically we share examples and some of these plugins and libraries and templates to get started. There's a bunch of examples in there that is good to get started with. And the hub QR code is still here. By the way, that QR code is backed by a Spin application, because why not? That Spin application is on the hub as well. So that's that. We have a Discord server where we have a lot of great, I think we are closing in on 1,500 or 2,000 people on that Discord server at this point. So a lot of great stuff happening there, and you're more than welcome to join that. With that, thank you very much. I'll be here for questions afterwards. We brought a bunch of stickers that are on the table. And don't forget to join our workshop at 3 p.m. and you can get hands-on with Spin, and we'll just have fun writing code. Thank you.